Hello guys, so this video is about how to set up a simulation in Abaqus regarding the drilling operation in composites to study the delamination. Delamination is a hot topic when we talk about composites. So there are basically two methods. For the method that is the cohesive zone method, and it is divided into two ways. The first method is called as the cohesive element modeling, and the other method is called as the cohesive surface modeling. So today we are going to talk about the cohesive element modeling. It is widely used. It is a widely used model type in composites and in delamination. So we are going to thoroughly discuss about the process of setting up this simulation. So starting from the part model, first we need to create a ply. So 3D deformable solid extrusion, and then the approximate size we are taking as 1. This approximate size tells you about what will be the chart size. So 1 indicate that the chart that is going to appear after is going to be 1 by 1. Continue. So this is 1 by 1. So and whatever number you are entering, you must make sure that it must be inside this 1 by 1 box. For example, I have 70 millimeter size, so 1 is good for it because 70 millimeter and 1 refers to 1 meter. So now we are going to create a ply and then give it dimension and extrude it. Okay, so now the composites we are making is of the 7 plies with 6 cohesive element. The size of the ply is 0.2 millimeter, and the size of the composite is 5 micrometers. So now we need to make the partitions. Creating datum planes, flip it downward, so here one datum plane is created. Now we need to make 7 more datum plane with datum plane for cohesive element as well. So if we look, we need to flip it downward because we are going down. Now we will make datum plane for cohesive element, that is 5 micrometers. If you look closely, now 2 datum planes have been created. Now we will follow the same procedure till we make the total 7 plies with 6 cohesive elements. Okay, so now as you can see that 7 plies have been created. Now we need to make partitions. For that we need to use this thing, that is using datum planes. So first we need to select the datum plane. So the partition has been created. Now select the cells to partition, then again select the datum plane. So now as you can see the cohesive element, the partition for the cohesive element has been created, and we will follow the same procedure for the rest. So all the cohesive element has been created with 7 number of plies. So as you can see here, the partitions have been created, and along with the partition there are the cohesive elements as well. Now the next step is to assign properties. For that we will go to property module. Okay, so in property we need to assign 2 properties, one for the composite and other for the epoxy, or other for the cohesive element. So for that we need 3 properties: density. Okay, so since we are using the subroutine, so for that we need 3 properties: density, depth var, and user output variables. No. Okay, so not this one, it was user material. Okay, for the density of my composite is 1600 kilogram per meter cube. Depth var is basically how much SDV, solution dependent variable, is in my subroutine, and 5 is basically the number of the outcome. And the user material, okay, so for that I have given the properties in another CAE file, so we will take it from here. Okay, so you need to make sure the order is the same as the order in the subroutine. Okay, so the epoxy has been created. Now we are going to assign element for cohesive element. Okay, so create. Okay, so it is the type is traction, and the stiffness value we will see from. Okay, so the next property we need is the damage for the traction separation with maximum stress damage S. Okay, and here we need 2 criteria: damage evolution and damage separation. Okay, about the last stage, these are the stiffnesses along various direction. So we will see the properties from here. Basically these are the properties I have taken from research papers. So if you guys want it, I can share the papers with you. Okay, in this there basically we need to apply these 2 things as well. First one, we are considering the energy. So in the okay, so for damage evolution, we are selecting energy, that is 287. So it is 287. Okay, and we also need damage stabilization, and it should be a smaller value, 0.0001 E. Apart from it, we would be requiring density as well. The density is basically around 1300 for the epoxy. So now the properties have been assigned. Now we need to create section. Section is basically what it gives us that basically it is the assigning that what it will act like. So for CFRP, it will act as solid homogeneous, and the material is CFRP. Okay, and for the section 2, it will act as cohesive. Okay, and the material is epoxy with the response traction separation. Okay, so now we need to assign these values here. Okay, so in order to assign it, just click it. They are section 1. You can see material is CFRP. Okay, and then we need to assign for the epoxy. Press shift and then select. Done. Okay, so the section is section 2. Basically it is epoxy. Okay, so now as you can see, it will also become green. The next step in the property is the defining the orientation of the ply. So we are doing on 0, 90, 0. So these are the 0. We are using the default coordinate system. Angle is 0. Now we will give the orientation to the second ply, that is 90. Okay, so for part we also need a drill. So I have made a drill in the SolidWorks, so I am going to import it. Okay, so it needs to be in the step format. Okay, so it should be a discrete rigid with a scale is, so since I design it in meters, so I need to scale it down to the millimeters, because I am also using the millimeter for my ply. Once imported, you need to make certain things in it. First of all, you need to create it into a shell. Since it is rigid, so creating a shell will reduce the computational time and it will not affect anything. We need to make a reference point at the top of the drill, and then we need to create a set for the reference point. It will be used later in the process. Now we are going to the assembly, and then we need to assemble both the parts. If you auto offset it, it will be helpful. So first we need to select drill bit, so we are removing the composite for some time. Okay, so we need to select it from here. So we need to create a centroid on the composite, so we are selecting this thing. Okay, so as you can see, the centroid has been created. Now we need to translate that drill bit into this centroid. Okay, so again we are doing it. We need to remove this part, remove, dismiss, and then we need to translate it. Now it has been done. Okay, so I am rotating. If you press Ctrl Alt and if you press the left click of the mouse button, you can easily rotate it in any direction you want. Okay, step. So basically step is the, by step you give the type of the solver. So I am going to select dynamic explicit, since it is a very non-linear problem, and there is the application of the load, and the load being applied is not very small. It is being applied at a very higher velocity, and it's a non-linear problem. That's why I am selecting dynamic explicit. So general procedure is for the linear as well as non-linear problems, whereas linear permutation is only for the linear problems. Time period, you can get the time period from the formula. Distance is equal to velocity is equal to distance by time. So if you know the distance of the ply, the total distance that it will have to go through, divided by the velocity at which the drill is moving in downward direction, you will get the time. So the time in my case is about point, and then whatever the time comes, you need to multiply it by 2, because there will be some resistance when the drill is being creating a hole in the plies. So you need to multiply it by the 2 so that your simulation does not stop in the middle of the simulation. So it comes out to be 0.25, the double of it. Okay, so there is incrementation as well. You can fix it, and you can say that I want this increments. Mass scaling is another thing where you can increase the density of your material, reducing the computational time, but it can affect the practical assumptions. It can deviate your simulation with the practical, in real life it deviates your simulation from the real life behaviors. Okay, so field output variable create. So these field output variable will only give you the contours. So whatever you select here, it will give you the contours of that data. So it is better to select only those that will be that you only required. Do not select all of it, then it will take a lot of time in simulation. So these are my thing that I needed, so I am going to just paste it here, so it will automatically okay. Since we are using the subroutine, so it is necessary that we use the SDV as well as the status from the field output, state field output. Okay, so we want data to be at every x units of time, and x unit of time, we mean that if we have a step time of 0.25 and we want 100 data points, so every x unit of time means it will be 0.0025. So at every 0.0025 time of our 0.25 total time, it will record a data. It is best practice, but if you say that every time increment, then it will take a lot of time. If you say every space time interval and you put the value of, and if you put the value of the increment as 1, it also going to take a lot of time. So every x units of time and the number of data points you want, divide your total step time by that number, then you will have a control over the data points. Okay, similarly the history output are those output that give you the output data, but it will not give you the contour. It will give you the data so that you can plot it. So basically it gives you data for the plotting only, and it do not give you the contours. Whereas the field output, the data you selected in the field output, it will give you the contours of that data. So we need the thrust force and the torque and displacement in the z direction only, and plots for that. So that's why we are using only that thing. Okay, so similarly we'll every x unit of time, and our step time is 0.25, and we need 100 data points, so it will be 0.025, and it should be on this reference point, because it will tell us how far the drill has gone inside the ply and how much the force has been acting upon to the drill bit. So we are selecting the reference point from the set we have created earlier. So now the next step should be the meshing. We need to mesh both. So we are taking as 0.8 millimeter for this one, and it is rigid and it is undeformable, so meshing here will not affect the simulation result. However, the simulation result will be affected if you are not using a proper mesh on this ply, because it is going to deform. So we are going to create a region where there will be more action. Vertical and on the right, so it will rotate it in this manner, circle. We need to perform the maximum drill size is 6 mm, so we are taking this as 6.5 mm. Okay, so now we need to partition all the rest of this thing. Once partition, it will all appear as yellow. For that we will go here and select this one, select the okay, so select the cells to partition. We want all the sets to be partitioned. Now we need to select one of the edge, this edge, done, and then we need to extrude along a direction, and at which direction we need to extrude along. We need to extrude it in the downward direction and flip it, so it will be extruded and all will get yellow. Okay, so now we need to create a mesh, a final mesh on this region. So now you can see that all the partition have been created, done, and then let's say we are taking it as 0.25 millimeters. But you need to do the mesh convergence, and after that you can use that mesh. Okay, and then for the global we are going to select, let's say 1 millimeter, let's say 1.25 millimeters. The finer the mesh, the more time it would be required. Okay, so now the mesh has been created. As you can see, we have created a finer mesh on to the area where there will be more action, and on the rest of the region we have selected a coarse mesh to improve the computational efficiency. Now we are required to give the element type. For that we click here, and then we are going to give element type. The element is 3D stress, and we are selecting the wedge type element because it has some benefits over others, and the element, make sure to allow this thing, element deletion. Now for the cohesive element, we need to remove this thing so that we can get access to the cohesive elements. So for that we can go here and remove one by one. Done. Okay, so what we did, we do not select, we need to select the cells as well. Now it will remove it. Done. It will get removed. Now there are some partitions that also need to be get removed. So now the only thing we have left with are the cohesive elements. As you can see here, these are the cohesive elements. So we need to assign element type to it too. Select this element, done. And now the element type should be explicit and cohesive. Element deletion should be allowed, and it's a wedge element. Okay, done. The next step is to assign the orientation. For that we need to go here, select all of it, and then select the top plane like this. Done. Okay, so if you can see that the top one is brown and the okay, so it's not correct. So again we will select it and select the top surface. Yes, now the bottom should be purple. Now the bottom is purple and the top is brown, so it indicates that it is correct. You can further verify it by going to the tool, theory, and mesh stack orientations. When you click it, so it will show you no errors if your top surface is brown and the bottom surface is purple, and it also giving the instructions here as well. If it is not proper, then it will give you an error. Okay, now all is done in the meshing. Now we will go to the interaction. For interaction, it is a good practice first to go to parts and create sets for the nodes. In the node, select node. Okay, so that's why meshing is important before interaction, because we are needed meshes in creating the interaction. Select only that region that will be in interacting to improve the computational time. Also create a surface for tools. I am creating here because otherwise then it would be a long process. I have to remove the composite and then apply the surface to the drill bit. So it's a good practice to create sets and surfaces in the part module. Select brown. Okay, so now we will go to interaction. Okay, we need to create the interaction into one general contact, explicit, continue. Okay, so always self, and we need to create a interaction property. The interaction property is contact with two properties, tangential and normal. So in tangential we must give a penalty of 0.3 friction coefficient. Okay, afterwards, after that so we have created the property. Okay, in the second property, that is a surface to surface contact, explicit, we will select, and we will select initial, continue. So we need to create the first surface. For that is the drill bit, that's why we created the surface here, and the second surface is the node region, so that's why we created the node sets. Done. And in property 1, okay, so you will see that the interaction has been created, propagated, added, and you will see the master and the slave surfaces. So now you can see here both the surfaces have been created. Okay, there is one other constraint that you need to apply for the drill bit. For that you need to remove ply first. So remove it so that it would be easier. So we are applying a constraint of the rigid body. What is this constraint? This constraint states, okay, for the first we need to select the body region, so we are selecting whole the and for the point we are selecting the RP, reference point. So basically it says that whole the body of the drill bit is constrained by the reference point. So as the body moves, so by this constraint now the drill bit whole body will move with the same speed as the reference point. So it's a good constraint to be applied for drill bit. it means that the velocity of the RP as well as the velocity of that tip would be equal. Now in the final step we will create the boundary conditions, and in order to create the boundary condition we need the full assembly. Afterwards, for boundary condition there are two. First one is the boundary condition 1, system in constraint. Okay, so we are going to fix the sides and the face of the bottom for the drilling operation. You also need to select this. You have to be very cautious while applying the boundary condition, because if boundary conditions are not assigned properly, then it will show you errors in form of kinetic energy equals 0 in the job monitor. Whenever the kinetic energy comes 0, it must be because of the two reasons. Either the velocities are not applied or the boundary conditions are not good, they are not constrained properly. Okay, as you can see that all the faces have been shit. Now you need to do it again because you don't need to click anywhere else, otherwise you have to do all the operations again. Okay, so once selected, now you need to select here the face and then select the bottom face. Now you can see that all this is created, and you need to make sure that only the bottom circle is red. Okay, so if only the bottom one is red, done. Now you need to concentrate it. Okay, so now the boundary condition have been set with fix on the sides and only the face of the bottom is fixed. Now you need to create the second boundary condition, that is the velocity. Continue. So you need to make it in the initial first. Okay, so continue, and you need to select the reference point for it, this one. Okay, so it will get red. So we need the velocity in the z direction, that is v3, so we will not select it, and the rotation in the z direction. Okay, and then in the propagate we will now enter their values. It is 0.012 that I am taking meters per second, and it is 200 radians per second time. Okay, dismiss. So that is the boundary conditions. So all the thing has been set. Okay, so there is no property for it. Assembly, step, interaction, and then loads, mesh. Okay, job. Now we need to create a job 1, model 1. Okay, so in general, now here how we put the subroutine file, that is the method. So let's say there is your that is your VUMAT memory. We will use the multiple processors. The more number of processors you will engage, the more faster will be your computational. Okay, so it is one of the thing that you need to make note of, is that always use double analysis plus packager, because this sometimes this is good to reduce the computational efficiency, because the single precision does not give a good result, increasing the increment. That's why. Okay, then we need to submit it. Okay, so it says that already exists, so we need to change the name. Let's say job 11. Okay, then submit it. So once submit, you need to wait for some time, and after this I am going to show tell you some of the common errors that appear in the simulation. The first error that usually appear is the missing element, or you can say that the element properties are not defined, like that. So in order to solve that error, you need to go to the mesh, and you need to give the element type in the same way that I give to the cohesive elements. So you need to remove all the plies, and then you need to give the mesh element. Afterwards, the second error that occurs is the kinetic energy to be 0. So once the job starts, after some time you will see that kinetic energy coming 0, and this is due to the two reasons. The first reason is that the velocities are 0, the initial velocities are 0, and if it is not the case, the second is due to the fact if you constrain all your plies, and if you do not give the circle for the drill to pass through, and if you are fixing that circle as well in the bottom plane, that is the reason that kinetic energy comes 0. And the third error is basically appears when after some time you will notice that the increment is not, the total time is not increasing, so it is coming same, and this is due to the reason of the boundary conditions as well. So if you fix the bottom ply, no matter your upper plies are free, but if the bottom ply is fixed, then what will happen, that drill will not be allowed to get passed through, which in result drill will not pass through, and the total time will get stuck at one place. So guys, results have come, and if I see the results, so as you can see the kinetic energy is something and it is not 0. So if it's coming 0, so it means that it is an error. So my kinetic energy was also coming 0, but then I reapply the constraints. So when you are applying the boundary condition, you need to make sure that for example, if this is my boundary condition, so if I am applying my boundary condition, so for example, if you select this one, so when you are selecting the middle one, So make sure when both the edges are below. For example, now the both edges are below, now press shift and then click, then it will get selected. But if somehow you click the edge and then you click the middle part, then this thing causes error. So you need to be very careful when you are selecting the boundary condition. So that's it from the video, and I hope that you guys will be able to set up the simulation for the cohesive element. Okay, so thank you guys, bye bye.